Okay, let's consider this problem. This problem is a beam problem again, but this is the end product beam, and at the right end, it's just not the free end. It is supported by the spring element like this. Okay, and on the left hand side is fixed, and at the middle length is supported by the roller. Okay, so according to this, we may discretize the element into just 3 elements. For this case, we will this type to be 3 elements. Just for beam element, it's just two. It's just like we have 2 beam elements and 1 spring element. Okay, we may set up the global coordinate is maybe like this. Is x, is y. Okay, but we have to consider in local coordinate also. For the element, for the beam element, it is the same as the global coordinate. This is for node number 1, this is for node number 2. And for the local coordinate, it's just y and x. Okay, it's just in the same direction. And for element number 2, that is the beam element also. Okay, but for element number 3, that is the spring element. The spring element, we have to consider that the spring is in this direction. So what does it mean? It means that the local coordinate of the spring, if we just a little bit review for the spring element, you see that the spring element, we have 2 degree of freedom rate. This is D1. And it's just only axial rate. This is D2 for spring. If this spring is node number 1 and node number 2, the local coordinate is in this direction, right? But right now, we have the spring element that is the node, the starting node. It should be the node number 3, right? If we starting that, is node number 3. This starting node. The end node is just node number 4. Okay, so that means the positive direction of the nodal displacement and nodal force for the spring element, in local, it should be in this direction. This D3, okay, and this is D4. Okay, so according to this, we will mention that it's also for the force F3, okay, and the force F4, like this. Okay, so according to this, the element stiffness, it should be K minus K minus KK, right? Okay, we will starting with the forming the element stiffness first. For the stiffness of the beam, we know that the element stiffness of the beam is maybe, if we consider the term just like, thing we have, should mention it again. Okay, so for the beam element is equal to EI over L cube. Okay, just 12 6L minus 12 6L 4L square minus 6L 2L square 12 minus 6L and also 4L square, right? This is symmetry. Okay, but for the spring, it is K minus K minus KK. Okay, in order to working together, we can simplify the spring element. That is actually which should write in the similarly term of the beam element also. That is, we have to include EI over L cube into the spring element. So how can we do that? This is for K spring. For this case, just for only this case, it just should be EI over L cube, right? And it should be K. Okay, and divided by EI over L cubed, this is become L cubed over EI instead. Okay, and this actually it is a similarly term. Okay, when we do it. Okay, but it is in for more convenient to include it in the stiffness of beam element that is compatible with the displacement in for node number 3, that is we have d3y. Okay, like this. Okay, for this we can assembling the element stiffness together, and we found that for 2 beam, actually we have just only this term, right? And after we combine with the spring, that we include this term into the metric, into the system. Okay, and now we obtain 1, 2, 3, 4, 5, 6, and 7. Okay, 7 by 7 stiffness matrix. This is for the global stiffness matrix. Okay, and after that, okay, we can define this term to be just K palm. Okay, we can define this term in order to simplify the writing to simplify the writing. Okay, so the notation K palm is applied in order to simplify the term. Okay, so right now we have the system, the global equation of the system, and we apply the boundary condition. Boundary condition is what? Boundary condition is just d1 y and v1 are 0, right? And this is d2y are 0. Okay, and d4y 0. Okay, d4y 0. So when we apply this boundary condition, so the stiffness, the system of 7 by 7 is reduced to 3 by 3 like this. And from these 3 equations, we can solve it analytically. Okay, we can solve it analytically and we obtain the solution like this in the formula. Substitute the value, the given value, the constant, into the equation, we obtain the solution, that is d3y is equal to this, and phi2 and phi3. Okay, so this is the solution that we already have. Okay, so according to this, when we substitute this value back into this equation, okay, we can obtain the nodal force. That is the same procedure, right? After we obtain the nodal force, what does it mean? It means that at the nodal force, we have the force at node number 3 just equivalent to the applied force, that is minus 50 kilonewton, that is equivalent to the applied load. And for F1y is the reaction force. The negative sign means that it is downward. Okay, so for F2y, that is the nodal force at node 2 is positive, so it means that it is upward, right? Okay, so the bending moment at node 1 and node number 1, what's happened? It is negative also. Okay, so because it is negative, so it means that the moment it should be like this. Okay, because it's negative. Okay, it is clockwise. Clockwise. For this case, it is clockwise. And for M2, M2 is equal to 0 because it is the roller. Okay, and then for M3 is 0 also. M3 is 0 also. For this case, it's just for this case only. Okay. So, and we can find the spring force. The spring force that is for F4Y. F4Y is obtained, that is equal to 3.5 kilonewton. Okay, 3.5 kilonewton. The negative sign is shown in negative sign. Sorry, this is the negative. It's come from what? It's come from the stiffness that is over here. That is K palm minus K palm. Okay, and multiply with K3Y. Okay, we will obtain like this. Okay, so according to the negative sign of the formula, we will get the positive sign of the force. That is mean that it is upward. Okay, so according to this, from this force, we can draw the free body diagram of the beam that we can obtain like this, and we can check the equilibrium of the force by using this free body diagram. Okay, so that's all for this example.